Okay guys, welcome to my lesson. If you are new to this channel, you are most welcome. On this channel, I teach physics, chemistry, biology, mathematics, and also revise past paper questions. Please enjoy the lesson as I promised you. If you haven't considered subscribing, please subscribe now so that you don't miss on my next video, where I will be revising 2020 GCE Science Paper 1 and Paper 2, showing you the way to distinction. So in today's lesson, we will be revising Science Paper 1, 2021 Examination for General Certificate of Education Ordinary Level. Let's go straight into the lesson. Okay, so let's look at section A, which consists of 20 marks, 20 multiple choice questions. In this section, they say answer all the questions on the answer grid provided in this question paper. A1 reads, the following dimensions of a metal sheet were measured by a welder using different instruments. So the welder measured the length, which was 40 centimeters, the thickness, which was 0.05 millimeters, and then the width, which was 8 centimeters. Then the question reads, which instruments were used to accurately measure the dimensions? A. Meter rule, length meter rule, thickness micrometer screw gauge, width meter rule. B. Length meter rule, thickness vernier caliper, width vernier caliper. C. Length micrometer screw gauge, thickness meter rule, width micrometer. D. Length meter rule, thickness engineer's caliper, width micrometer screw gauge. So here, what they're saying is length. What was used to measure length here, which is about 40 centimeters? Actually, we use a large, or rather measuring instrument that are a little bit big to measure such length like this one also, which is about 40 centimeters. And here we are told the thickness of this material here, of this metal sheet here, is 0.05 millimeters. So we use an instrument which is suitable for measuring very, very small distances like this thickness of 0.05 millimeters. And this width here, it's about 8 centimeters wide. So this is quite a large distance also, in which we need a suitable instrument that can measure this distance accurately. So looking at this, the welder here used a meter rule. Then here he used a micrometer screw gauge, because a meter rule cannot measure the smaller distance of 0.05 millimeters. Also, a micrometer screw gauge is the one suitable for measuring such distance. Again, a vernier caliper cannot measure this distance, because the least count, or the smallest distance that a vernier caliper can measure in millimeters, is just 0.1 millimeters. So this means that a vernier caliper can't measure this. Then this width here can't be measured by a vernier caliper, because it is out of range of distance that can be measured by a vernier caliper. So now, looking at our answers, the best answer here is A. So length was measured by meter rule, thickness was measured by micrometer screw gauge, width was measured by a meter rule. So the answer is A. Then let's go to 2. 2 reads, the following diagram shows a simple pendulum. The following diagram shows a simple pendulum. So we have a bob here swinging this way and coming back. Then the string there. Then they are saying what physical quantities can affect the period of the pendulum. What physical quantities can affect the period of the pendulum? So the only physical quantities that can affect the period of the pendulum are actually gravity and length. So here let's check the mass of the bob and the length of the pendulum. No, the mass does not affect the period of the pendulum. Then B, the length of the pendulum and the acceleration due to gravity. Yes, the answer is B. Let's go to 3. 3 reads, a student weighed a small amount of sugar crystals and found the mass to be 0.568 grams. After adding 2 small sugar crystals, the mass was found to be 0.571 grams. Assuming that the sugar crystals were identical, what was the average mass of one crystal? All right. So, okay, the student here measured the mass of some sugar crystals and found them to be 0.568 grams. Then he added 2 small sugar crystals. The mass was found to be 0.571 after adding 2 crystals of sugar. Assuming that the crystals were identical, what was the average mass of one crystal? So for us to know the average mass of one crystal, we have to subtract this initial mass from this, and then since there were 2 crystals, divide by 2. So here we'll say 0.75 minus 0.568. Then the value that we'll get is this. Then that value that we got, we divided it by 2. So when we divided it by 2, we got this one. Then when writing it in standard form, you'll find that we have to move 2 steps, 3 steps this side. 1, 2, 3. So which will be 1.5 times 10 to the power negative 3 grams, which means our answer is supposed to be A. So let's go to 3. 3 reads, the following graph shows the distance. The following graph shows how distance varies with time for a cyclist's ride that lasted for 250 seconds. The following graph shows how distance varies with time for a cyclist's ride that lasted for 250 seconds. So this is the graph. This vertical axis represents distance. Then the horizontal axis represents time. So let's analyze the graph. So from here 0, distance was changing with time, meaning here the object was moving. Then at this point, the graph is now horizontal, which means that here distance wasn't increasing when time was still moving. So here the cyclist was stationary. Then again at 150 seconds, again the graph started rising upwards, which means that the distance also started changing with time. Now the question reads, what is the cyclist's average speed for the whole journey? What is the cyclist's average speed for the whole journey? So here, average speed is calculated from total distance divided by total time. So looking at our cyclist here, the total distance that the cyclist covered is actually 300 here. However, when we look at our total time, the total time can't be 250 because at this point from 100 second to 150 50 seconds, the cyclist actually here was stationary, okay? The cyclist wasn't moving because he was stationary. So which means that this time here is not going to be considered. From 100 seconds to 150 seconds, we are not going to consider this time. So meaning he's still at 100 here. So then from here now, that's when he started moving again. So from here to here, it's 50. From here to here, it's 50. So meaning from here to there, it's actually 200. Then 200, I mean 100. Then 100 plus 100 here, it will be 200. So the total time that the cyclist consumed in his journey when he was moving was actually 200. So the total distance that the cyclist covered is 300. So we'll get 300 divided by 200, which gives us 1.5 meters per second as our answer. So let's go to question 5. Question 5 reads, the diagram shows a car going round a bend at a constant speed. The diagram shows a car going around a bend at a constant speed. So this is a car going around this bend here, or the circular path. This is the center of the curve, or going around this curve. Excuse me. Which statement about the car is correct? Which statement about the car is correct? A, there is no resultant force acting on the car. There is no resultant force acting on the car. B, the car is not accelerating. The car is not accelerating. Then C, a force of constant size acts on the car towards the center of the curve. Or then D, a force of constant size acts on the car in the direction of motion. So for this car to continue moving in a circular path, unless there's a force trying to cause it to move in that circular path. So that actually force, it is constantly acting on it to maintain it going in that circular path. And that force actually points in the center. So when I look at this is actually not true. B, where they say the car is not accelerating, is not true, because acceleration is the change of an object's velocity. So since velocity deals with direction and the car's direction is changing, that means also the acceleration of the car is changing since the direction is changing. So this is not true. Then let's also see D, which says a force of constant size acts on the car in the direction of motion. So they're saying there's a force that is acting in that direction, which is not true. The force making it to move in this circular manner is the force that is directed towards the center. So this now leaves us with two options, which is there is no resultant force acting on the car. So no resultant force acting on a car. There is actually a resultant force, I'm sure, which is causing it to continuously move. However, this one C says a force of constant size acts on the car towards the center of the curve. I think this one was the best answer, even though this one sounds to be the best, but this one is the best answer. So let's go for 6. 6 reads, in a small hydroelectric power station, 20 kg of water flows through a vertical height of 15 meters in 1 second. If the efficiency of the power station is 60%, and taking G as 10 Newton per kg or kilogram, what is the potential or what is the power output of the hydroelectric power station? So let's read again. A small hydroelectric power station. In a small hydroelectric power station, 20 kg of water flows through a vertical height of 15 meters in 1 second. If the efficiency of the power station is 60% and taking G as 10 Newton per kilogram, what is the power output of the hydroelectric power station? All right, so now for us to be able to calculate the power output of the hydroelectric power station, we need to use the efficiency formula, which says efficiency is equal to power output divided by power input times 100%. So this is the efficiency equation. Then we are told the efficiency E here is equal to 60%. Then they are asking us to calculate the power output of the hydroelectric power station. So we need to know first of all what the power input is, because we cannot solve this without knowing at least 2 of the physical quantities. So here, first of all, we need to calculate the power input. So power input is actually generated from the water that is falling through a vertical height of 15 meters in 1 second. So here we'll say power input is equal to work over time. That is the formula for power. Then work here is found by 20, which is the mass of the water, times 10, which is the acceleration due to gravity, then times 15, which is the height, because work is given by force times distance. So force is here 20 kg times 10 gives us force, and this is the distance here, then divided by time, which is 1 second. Then this gives us our power input to be 3,000 watts. So having found our power now, we are now going to make power output the subject of the formula as shown. So power output is equal to efficiency times power input over 100. Then we'll substitute. Okay, what I've done, I've just made this the subject of the formula. So if you are not sure how I did this, you can also make a request in the comments, so that in my next video I will show you how I made power output the subject of the formula. So now we are going to substitute. Where there's a E, we put 60% as efficiency times power input, which is 3,000 watts over 100%. Then after evaluating everything, our power output is 1,800 watts, which is B. Then let's go to 7, which reads, the following diagram shows 4 identical metal cans E, F, G, H, whose outside surfaces were painted as identical as indicated. Equal volumes of water at a temperature of 80 degrees Celsius were placed in the cans here. So this can is painted black and it's open, and there's water which is at 80 degrees Celsius. Then also white can which is open there's water which is at 80 degrees Celsius. Then we have another black can which contains water which is at 80 degrees Celsius, but it is closed with a lid. And also we have another white can containing water which is at 80 degrees Celsius, but also closed. Now the question reads, after 5 minutes in a cool room, which metal can would contain the coolest water? So after 5 minutes in a cool room, which metal can would contain the coolest water? So here, what they're trying to do is, after this water, putting it in a cool place, we expect it to start cooling. So which one of these cans here will have the coolest water? So the answer is A, because black substances are good emitter. They release heat quickly to the environment, and also they are good absorber of heat. But in this case, they are not absorbing, they'll be losing since they have been put in a cool place, and since it is open, so it is going to lose more heat through the open and through its side since it is painted black. However, these, since they are actually let's see, yeah, since these are white, so white, they do not lose heat quickly or also gain heat quickly. So meaning they are not good absorber, and they are also not good at losing heat. So this one will lose, but because it's open, but since it is white, it will not lose as much as the black can. These, since they are closed, this one is closed, so it won't lose through the opening here, but just through its body. But this one also will lose, but will lose, but not much, because it is a white can, and since it is closed, there will be no heat that will go out through its opening. So the answer here is A. Then 8 reads, a crest of a water wave travels 0.4 meters in 5 seconds. If the distance between two successive crests is 0.005 meters, what is the frequency of the wave? So a crest of a water wave travels 0.4 meters in 5 seconds if the distance between two successive crests is 0.005 meters. What is the frequency of the wave? So what I did here is I said, if this water wave travels a distance of 0.4 meters in 5 seconds, and then we are told that if the distance between two successive crests, which is the wavelength, is 0.005 meters, then what is the frequency of the wave? So first of all, I had to know how much time it would take for a wave to travel a distance of 0.005, which is a wavelength. So here I said 4 meters travels actually 5 seconds. So 0.4 meters is 5 seconds. Then I said, how about 0.005 meters will travel what seconds? I said x, then I multiplied, then I got this. Then I divided both sides by 0.4 to get x. Then I discovered that x was 0.065 seconds. So 0.005 meters would travel a distance of 0.0625 seconds. So this time is the time that is needed for this water wave to travel the distance between two successive crests, or it is the time needed to make a complete wave. So this time here, it is known as the period, because it is the time that is needed to make a complete wave. So a complete wave is the distance between two successive crests. So then I said, okay, then frequency, since is found by 1 over time, which is period, then I substituted over this one as the period. Then I found the answer to be 16 Hz, which is D. Then 9, an echo sounder in an aeroplane receives an echo from the ground 20 seconds after it was sent. If the speed of sound in air is 330 meters per second, how high is the plane above the ground? So an echo sounder in an aeroplane receives an echo from the ground 20 seconds after it was sent. If the speed of sound in air is 330 meters per second, how high is the plane above the ground? So what they did, this plane sends a signal from the plane, it goes to the ground. When it goes to the ground, it comes back. They receive the echo, the sounds that comes back. So now the time which it takes for this echo to go and come back is actually 20 seconds. So meaning now they're asking us to find the distance. They are saying if the speed of sound in air is 330 meters per second, how high is the plane above the ground? So they need the distance between the ground and the plane. So we know that speed is equal to distance over time. And now we want distance. Distance is equal to speed times time. Now, this time here, we divide it by 2 because it is the time that was recorded when the echo went and came back. But we only need the time for just one way. The time for one way, unless we divide this one by 2 to get 10. So we'll multiply here now that distance is equal to speed, which is the 330 here, times time, which is 10, so that we'll get our distance as 3,300 meters, which makes our answer to be D. Then 10, the following diagram shows the formation of image I from object O using a convex lens. The following diagram shows the formation of image I from object O using a convex lens. So not drawn to scale. So this is object. When the rays goes into the convex lens, they are refracted, and where they intersect here, that's where the image is formed. Then the question is, what is the focal length of the lens? So focal length is the distance from the focal point to the center of the lens. That's what they need here. So which we can calculate here as using this equation. So equation says 1 over focal length is equal to 1 over u, which is the distance of the object from the center of the lens. So this is the object, this is the center of the lens, the distance is 45 centimeters, then plus 1 over v, which is the distance of the image here from the center of the lens. Then when we substitute, now we make f the subject of the formula, which is the focal length. We get this formula, and then we substitute. Where there's u, we put 45 times where there's v here, which is the distance from here to here, which is 53, over the same u, v, 53 plus u, 45, and we get our focal length as 24. So looking at our answer, the answer which was actually closest was B. And actually, if you look at this one, actually we never even needed, I think, to calculate, because the distance from the focal point here to the center of the lens is the focal length. So the answer is B. Then 11 reads, where is the image in a long-sighted eye formed, and how can the defect be corrected? Where is the image in a long-sighted eye? Where is the image in a long-sighted eye formed, and how can the defect be corrected? So here they are talking about those people that have got problem with the eyes. Some people are short-sighted and some other people are actually long-sighted. So the people that are long-sighted, like this one, long-sighted, meaning that they can't see things at a long distance. So why is because the rays, when they enter into the eyes, the pupil actually converges them before actually they reach the retina where the image is supposed to be formed. So now such kind of problems, how can they be corrected? So we can use a convex lens which actually scatter them a bit to allow them to form on the retina. So here we said in front of the retina and focused by means of a concave lens. Yes, a concave lens which can actually, the rays before they converge, they are actually made to converge at a longer distance. So by doing so, they are allowed to converge at the retina where the image is seen. So 12, the following diagram shows the pattern and direction of the magnetic field between two magnetic poles J and K. The diagram shows the pattern and direction of the magnetic field between two magnetic poles J and K. So we have J and K, and we have these magnetic fields flowing from K to J. Then the question is, which type of poles are J and K? So we know that magnetic fields move from north to south, So meaning K is north and J is south. So K north, J north, wrong. K south, wrong. K north, yes. J south. So our answer is C. Then let's go. 13 reads, two spheres are mounted separately on insulating stands. If both spheres are positively charged, which diagram shows a correct electric field pattern? Two spheres are mounted separately on insulating stands. If both spheres are positively charged, which diagram shows a correct electric field pattern? So if they are positive, then field must be coming from the charge and they must be repelling. So since they are both positive, the field must be coming from the charge, like this one. It is coming from the charge going outward. But since they are both, here it is also supposed to be going outward. Now here it is going inward. So this is not true. Then B here, this one is going inward, which is not true. And this, so the whole of this one is not true. Then you see this one is going outward, this one outward, this one outward, 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 outward. And here there are no field, meaning they are repelling. So this one becomes the best answer, because here it is showing they are going inward, which is not true. These two are going inward. So our answer is C. Then 13 or 14 reads, the diagram shows a resistor connected to a cell of EMF 2 volts. The diagram shows a resistor connected to a cell of EMF 2 volts. How much heat energy is produced in the resistor in 6 seconds? So how much heat energy is produced in the resistor in 6 seconds? So our formula for calculating energy, they just need energy. Energy is equal to voltage squared times time divided by resistor. So we have been given voltage 2, time 6 seconds, resistor 5. So we just substitute 2 to the power 2 times 6 over 5 and get our answer as 4.8. So our answer is C. Then 15 reads a 2 kilowatt stove, a 0.2 kilowatt television set, and a 0.1 kilowatt lamp are all switched on at the same time. What is the total cost of running these appliances for 4 hours at 2 kwacha per unit? So a 2 kilowatt stove, a 0.2 kilowatt television set, and a 0.1 kilowatt lamp are all switched on at the same time. What is the total cost of running these appliances for 4 hours at 2 kwacha per unit? So here they need the cost of using this. So first of all, we need to add the total power that they're using, and then we'll see the formula. So the formula for cost is equal to energy times price. The energy times price. So now, here energy is found by power times time. So energy is found by power times time, then times now this price. Now power, when we add this, we'll get 2.3. And the time here is in hours, 4 hours. Then our price per unit is 2 kwacha. So we'll substitute like this. So when we multiply 2.3 times 4 times 2, we get our answer as 18 kwacha for ngwe, 18 kwacha for ngwe, which is D. 16 reads, a small coil is connected to a galvanometer as shown. A small coil, this one, is connected to a galvanometer as shown. This is a galvanometer. Then they are saying what happens to the pointer of the meter when the magnet is pushed into the coil. What happens to the pointer of the meter when the magnet is pushed into the coil? The pointer, so they are saying if the magnet is pushed in a coil, what will happen to this? Of course, since this is a galvanometer, and since this is a magnet, as it is pushed here, it is going to cut a wire, and then it is going to induce a current here. So this one will deflect. Now they are saying A, the pointer deflects to the left and then returns to 0. Then B, the pointer deflects to the right and then returns to 0. Then C, the pointer gives a continuous reading to the left. Then D, the pointer gives a continuous reading to the right. So these two are actually wrong, because according to electromagnetic induction, current can only flow here as long as the magnet is moving, but when it is pushed and it remains at rest inside here, there will be no current. Current will only move or show here as it is moved in. When it rests inside there stationary, there will be no current, And again, when they pull it this way or this way, again, there will be a deflection or movement, but in the opposite direction to the first one. So now here, the correct answer should be A. When it is pushed here, what will happen is current will start flowing in that direction. Why? Because according to Lenz's law, the current induced in the coil by a magnet is or flows in a direction to produce a magnet in itself that tries to resist the next coming magnet. So that current here, it will produce a magnet here. So this side will be a north. So north will repel with this north. But since this person will still continue pushing it, it will go in and the current will go like that. And this one tends also to face in the direction of current. So the answer should be A. Then 17 reads, which graph shows the voltage output V against time T for an AC generator? So an AC generator produces alternating current, the current which moves forward and backward. So a graph which shows how voltage output varies with time is D. 18 reads, the following diagram shows the appearance on the screen of the alternating voltage applied to the output of an electroscope. The sensitivity is set to 3 volts per second per meter. What is the maximum voltage? So they are saying the diagram below or the following diagram shows the appearance on the screen of the alternating voltage applied to the input of an electroscope. The sensitivity is set to 3 volts per centimeters. So this is the output of an alternating voltage when it is put to the input terminals of an electroscope. This wave is seen like this, and in the electroscope they have set the sensitivity to 3 volts per centimeter, meaning 1 centimeter represents 3 volts. Now they're saying what is the maximum voltage? So the maximum voltage should be from this center to the highest there, or from this center to the lowest point here. So we count how many these are there, centimeters: 1, 2, 3, 4. Now since 1 centimeter is 3 volts, how about 4 centimeter, which will be 3 times 4, which will be 12. So here we said 1 centimeter is 3. How about 4 centimeter? So when we multiply this times this, x, so this times that, 12 volts. So our answer was D. 19 reads, radioactive iodine is used to treat tumors of the thyroid gland. It decays by emitting beta particles and gamma radiation. The beta decay process is represented by the following equation. So let's read. Radioactive iodine is used to treat tumors of the thyroid gland. It decays by emitting beta particles and gamma radiation. The beta decay process is represented by the following equation. So this is the equation that represents beta decay. Then they are saying what is the nucleon number, that A there, and the proton number, this number here, for this nucleus of Xe. So here, for you to be able to answer this question, unless you know the general equation for beta decay, which is this. So the general equation for beta decay says if an atom is to undergo beta decay, it should produce another atom, but that atom, its atomic mass should be the same as the previous one. However, its proton number should be increased by 1, or should be larger than the previous one by 1. Then plus a beta particle which has 0 mass number and negative proton number, all right, or atomic number. So this simply means that the mass number should balance. The mass number on the left side of the arrow should be equal to the mass number on the right side. So if I say A plus 0, it's A. If I say Z plus 1 minus 1, I'll remain with Z. So here also it's Z, it's also A. Now they're saying this is the general equation which will help us to know this. So if this has undergone beta decay, we expect these masses to be the same as here. So here A will be 31. However, Z here should increase by 1, meaning this number here should be increased by 1. So 53 by 1, which is 54. So A should be 31, then Z should be 54. So let's look at our answers here. A number, nucleon number 78, not true. Proton number 53, not true. Not true. So proton number here, Z, will be 54, true. Then nucleon number, which is this one here, A, will be 131. It will be the same. So the answer is this. Oh, I had to even put it here where I said this will mean 131. Since it's the same, it will come here. Then here, this one should be increased by 1 as stated here. So this one increased by 1, it will go to that one. So 131, 54. So here, 131, here, 54. So 54, 131. So our answer is C. So 20 reads, a radioactive isotope has a half-life of 6,000 years. How much time passes before the rate of emission from a sample of this isotope falls to half of the original value? So they are saying a radioactive isotope has a half-life of 6,000 years. How much time passes before the rate of emission from a sample of this isotope falls to 1/16 of the original value? So they want to know the total time that it should take for that radioisotope, which has a half-life of 6,000 years, to fall to a value before that value actually reaches this. So what we are going to do here is to assume the original amount of the sample, because here we haven't been told the original amount of the sample. So the original amount of the sample here is going to be assumed to be equal to 1. So assume original amount of sample is equal to 1. Then we are now going to look at the remaining amount of sample. The remaining amount of sample, or the final amount of the sample. So here we'll say final amount will be now 1/16 of what was there, which will be equal to 0.0625. So this is gotten from here, 1/16 of the original amount. So now the original amount here was assumed to be 1. So we say 1/16 of, which is multiplication times 1, we get 0.0625. So this is the original amount. This is what remains. So now we want to find out how many half-lives had taken there, or had happened for this amount to decay from 1 to 0.0625. So we are going to do it in a smart way like this. So if you have an original amount of 1, so it would take 6,000 years for it to half, because 6,000, which is half-life is the time taken for half of a radioactive material to decay. So it is the time taken for half of a radioactive material to decay. So the original is 1. So for 1 to half, the time that it should take is 6,000. So we are going to say, so it will decay half of 1 will be 0.5. So 0.5 again will decay by the same amount, 6,000, and half of 0.5 will be 0.25. Again, this 0.25 will half by the same time, 6,000, to go to 0.125. Then this 0.125 again will decay by half by the same time, and then it will go to 0.0625. So this is now how it is going to decay to move from here to 0.0625, which is the final amount here. Now the question just says how much time passes before the rate of emission from a sample of this isotope falls to 1/16 of the original amount. So before it falls to this, which is this, how much time has passed? So we are not going to consider this time which it has taken to fall to this. This time will be excluded because they're saying before. So before is here. So meaning the total time will take this one plus this one plus this one, which will be 18,000. All right. So now at this point, we are going to go to section B. So if you are finding value in this video, please consider subscribing and also consider hitting the like button there, and also comment. It will encourage me to do even more. All right, so guys, let's continue with our video. Okay, let's continue with section B of our revision of science paper 1, and section B consists of 45 marks. And here it reads, answer all questions in this section. Write your answers in the spaces provided in this question paper. So you need to write your answers in the spaces provided like these in this question paper. So let's go and start with B1. B1 reads, figure B1.1 is a diagram showing the reading of the Vernier calipers. Figure B1.1 is a diagram showing the reading of the Vernier calipers. So this is a Vernier caliper showing some readings here. Then A, what is the reading shown on the Vernier calipers? What is the reading shown on the Vernier calipers? So for you to be able to know the reading, you need to have a formula which is needed to find the reading here on the Vernier caliper. Excuse. So the formula is reading, R for reading, is equal to MS, which is main scale, plus, open brackets, VS, which is the Vernier scale, multiplied by LC, which is least count. So least count is the smallest size that a particular apparatus can measure. It can be mass or length. So the smallest size that a Vernier caliper can measure when it is in centimeters is 0.01 centimeters. When it is in millimeters, it is 0.01 millimeters, 0.1 millimeters. So now, for us to be able to read this, we need to know the MS, which is the main scale, and also the Vernier scale. So the main scale is this top part here. These readings on the top of the Vernier scale, they represent the main scale. Then the Vernier scale are these readings at the bottom. These here, they represent the Vernier scale. So when reading the Vernier caliper, you need to read first the numbers on the main scale, the readings on the main scale, starting from left, going to the right. And as you read from left to the right, you don't need to exceed your reading this line here. You need to read up to this point here. You don't need to exceed this line down here. So you read the values on the main scale from left to the right before the line that is on the Vernier scale. So before you read this, you need again to study how these lines here are meant to mean, or what they represent. So here we have 5, 6. So the line in between here should represent 5.5. How about these smaller ones? So if this one is 5.5, this means this is 5.1, 5.2, 5.3, 5.4, 5.5, 5.6, 5.7, 5.8, 5.9, 6. Continue the same way until you reach here. So since we are supposed to read up to this line here, we don't need to exceed beyond this line. We have just to end here. So our value will be 5.1, 0.2, 0.3. So that's where we'll end. Our main scale will be 5.3. Then again, now we'll read the Vernier scale here, which are these values at the bottom. Again, we read from left to the right, and we consider this edge of this Vernier scale here to be the 0. So if this is the 0, this should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. However, when reading here, again, the rule is you look for a line on the Vernier scale, these lines on the Vernier scale, that aligns up with a line on the main scale. So you check the line on the Vernier scale that aligns or appears to be in a straight line with another line on top here. So what you are going to do is to start inspecting them one by one. When you look at the first line, it doesn't align up with anything here. When you look at the second line, it doesn't align up with anything here. When you look at the third one here, it lines up with this one here. So when you check any other line, there's nothing that line up like it does here. So meaning when reading, starting from the left going to the right, when you read, you have to end where the line makes a straight line like here. So meaning when reading here, you start from 0, this one, 1, 2, 3, you end here. So meaning our Vernier scale is 3, and you don't put units on it. So when you substitute these values, this you put it here, this you put it where? Here. Then this, since it is in a centimeter, this you put where? There. You have this. Then you are going to multiply. First of all, brackets of division, multiplication, addition, and subtraction. BODMAS must work. First, multiply what is in the brackets, which will be 3 times 0.01, which will give you 0.03. Then add to 5.3, which will give you 5.33 centimeters, like that. So this is our reading, which we are going to place here. Then B says, B1 says, convert the reading in A above to meters. So convert the reading here in meters. So we know 1 meter is equal to 100 centimeters. How about 5.3 3 centimeters? So for you to get this one into meters, you divide it by 100 and you get a value of 0.0533 meters. All right, so let's go. Then 2, they are saying write the reading in B1 in standard notation. Write the reading in B1 in standard notation. So in B1, the value that we found in meters was this. So they are saying we write it in standard notation. So what they mean is to remove the zeros here in front. So how do we remove these zeros? We shift the point to the right. So we shift it how many times? 1, 2. When it reaches here, the zeros would have moved out. So since you shift it 1, 2, then you have to multiply it by 10 to the power. How many times did you shift it? 2. 2 to the power 2. Since you were also shifting, going in the right direction, so going in the right direction means negative. That power you put in negative. I hope you are getting this. So our answer now will be 5.33 times 10 to the power negative 2 meters. Then part 3 reads, how many significant figures does the Vernier calipers reading in in meters have? How many significant figures does the Vernier calipers reading in meters have? So these readings here, how many significant figures are there? You count these figures themselves as they appear. So it has 1, 2, 3. 3 significant figures. B2 reads, a man of mass 75 kilogram on Earth goes to the moon where the gravitational field strength is 1.6 Newton per kilogram. Excuse me. A man a man of mass 75 kg on Earth goes to the moon where the gravitational field strength is 1.6 Newton per kg or kilogram. A, what is the mass of the man on the moon? What is the mass of the man on the moon? What you should know here is that mass does not change. Mass remains the same. So here we know that mass remains solid with this is. It's not supposed to be there. Yeah, so mass remains the same in all places in the universe. So since mass remains the same in all places in the universe, that means mass will still be 75 kg only or kilogram only the moon. Then here they're saying B, what is the weight of the man on the moon? What is the weight of the man on the moon? So weight is a force which is given by weight is equal to mass times gravity. Since on the moon, the gravity acceleration due to gravity is 1.6 Newton. So and the mass is 75. So we'll say weight is equal to mass 75 times acceleration gravity, which is 1.6. Then when you multiply this, you get your answer as 120 newtons. Then C reads, a light truck of mass 2,000 kilogram accelerates from rest at a rate of 1.5 meters per second squared. A light truck of mass 2,000 kilograms accelerates from rest at a rate of 1.5 meters per second squared. Calculate the force required to accelerate the car at this rate. Calculate the force required to accelerate the car at this rate. So this is the acceleration, and we know that force is given by mass times acceleration, and the mass is 2,000, so we replace 2,000, and the speed here or the acceleration is 1.5, and when we multiply we get our answer as 3,000 Newton. Then B3 reads, figure B3.1 is a diagram showing a uniform meter rule freely pivoted at its center. A Newton excuse me, a Newton meter is hung 20 centimeters from the pivot, while a 4.0 Newton weight is suspended 4 centimeters from the pivot. So here we are told that figure B 3.1 is a diagram showing a uniform meter rule freely pivoted at its center. Here, pivoted here. Then a Newton meter is hung. This Newton meter is hung 20 centimeters from the pivot, while a 4 Newton weight is suspended 40 centimeters from the pivot. 40 centimeters from the pivot. Then they are saying the meter rule is in equilibrium. So A, state the principle of moments for a body in equilibrium. So if a body is in equilibrium, it means all the forces acting on it are balanced. So it can be rotating. If it is rotating, the rotation must be uniform, which means that the forces that were pushing for the forward are equal to the forces that have balanced with the forces that are pushing in anti-clockwise. So it remains in a state of constant rotation. Or if it just remains like this, where it is not going up and down, that means all the forces acting on it are balanced. So they want us to state the principle of moment for a body in equilibrium. So the principle of moment states that the sum of the clockwise moment is equal to the sum of the anti-clockwise moment. So for a body in equilibrium like this, the sum of the clockwise moment is equal to the sum of the anti-clockwise moment. So clockwise is going this way. So when you add all the moment taking it this way, plus the moment that take it this way, they are equal. So they are equal for any body which is in equilibrium. Or you can say that the sum of the forces acting on the object in equilibrium adds up to 0. The sum of the forces acting on the object in equilibrium adds up to 0, which is almost the same as the first one also. So when you add all the forces that are acting on this, they must add up to 0. All right. So now let's go to B. B says calculate the reading on the Newton meter. So they want us to calculate the reading on the Newton meter here. So since the Newton meter is hung here, that means that it is having a force that is trying to pull this meter rule in a clockwise direction like that, giving it a clockwise moment like that, or rotation. Then we have also this Newton here, which is hung. So this one is hung, meaning that it has a force facing in the downward trying also to give it an anti-clockwise moment in that way. So now they are saying calculate the reading on the Newton meter. So we have to write a free body diagram here that we analyze properly. So this is the meter rule, which is pivoted here on its center. Then we are going to represent a force in the Newton meter, which is pushing it upward there here as F2 or F1, sorry. Then we are also going to represent the distance of F1 from the pivot. This is the pivot as D1. Then we are also going to write this force here, which is acting downward here as F2, and then also indicate its distance from the pivot here, as in D2. Then, using the principle of moment, which says the clockwise moment, the force which is trying to take it this way, the clockwise moment, because the clock goes like this, must be equal to the anti-clockwise moment, the moment which takes it this way. So the moment which takes it this way, it is this one. This force times this distance must be equal to the moment which takes it this way. It's this force times this distance. So the moment will be, since this body again is in equilibrium, the meter rule is in equilibrium as stated. This means that the moment is going to be the force 1 times D1 is equal to F2 times D2. So for an object in equilibrium, this is the principle of moment. So what is trying to take it in this direction? Force 1 or F1 times D1. It's a moment which takes it in this one direction, and must be equal to, for it to be in equilibrium, must be equal to the force which is taking it this way, so that it remains stable. This is F2 times D2. Then we are told that F1, we don't know it. It's what we need to know, the force which it is reading here. Then we know that if we make F1, which we don't know the subject of the formula, our formula will be F2 times D2 divided by D1. Then now we should look for the values for F2. So F2, which is here, it is going to be, before we go for F2, we will put the distance. D1 is actually 20 centimeters from the pivot. Then also, we'll also say D2 is from the pivot also to the force is 40. Then F2 is 4 Newton. Then we'll substitute. Where there's F2, we'll put 40. Where there's D2, we'll put, F2 4, then D2 40, then D1 20. So we'll substitute, and our step will look like this: 4 times 40 divided by 20. Then after we do the evaluation, we'll find that our answer is going to be 8.0 Newton. So F1 is 8.0 Newton. So we'll write 8.0 Newton as our answer. And why I've put a 0 here is because of this value here. It has two significant figures, so it is important also to put 8.0 because we are being guided that the reading should be in two significant figures. All right. C reads, state with a reason whether the Newton meter reading would increase or decrease when the 4.0 Newton weight is moved to a distance of 30 centimeters away from the pivot. So here what they are saying is we state whether the Newton reading here would increase or decrease when this 4 Newton is moved at 30 centimeters away from the pivot. So since when this force is moved, that is going to affect actually also the reading on the Newton meter, because when the force is decreased here, you also consider that the moment which takes it this way will also decrease. So since the moment which takes it downward will decrease, so for it to remain balanced, even the moment which takes that other way should decrease to keep it in the balanced state. Otherwise, if this force here is moved this way, it will decrease the moment which takes it downward, and it may cause this thing to rotate in the clockwise direction. But to keep it maintained at equilibrium, this force also should decrease. All right, so the answer is the Newton meter reading would decrease because the anticlockwise moment will decrease, and to maintain the meter rule in equilibrium, the Newton meter should decrease also to decrease the clockwise moment. All right, so let's go to 4B4 reads a small hard ball of mass 0.14 kg is thrown vertically upwards and reaches a height of 12 meters above the point from which it is thrown. A small hard ball of mass 0.14 kilogram is thrown vertically upwards and reaches a height of 12 meters above the point from which it is thrown. A. Calculate the work done in lifting the stone to the height it attains. So here they made a mistake. It's not the stone. We are talking of a small hard ball. So calculate the work done in lifting the ball to the height it attains. So they want the work done. So we are now going to write, remember the formula for work done, which is work is equal to force times distance. Work is equal to force times distance. Then we are not given work, but we know that force is equal to mass times acceleration due to gravity. That's what we are supposed to know. When it is thrown upward, it will go there with an acceleration due to gravity. So the force will be mass given here times the acceleration due to gravity, which is always 10 newtons per kilogram. So since force is equal to mg, we are going to substitute in our equation. Where there is a force here, we will put mg, and d we will put back here. And then since this distance here is height, so we can also replace this d with height, because height is also distance. So when we replace with height, you discover that this formula for calculating work is similar to the formula for calculating potential energy. So in short, potential energy is also equal to the work done in moving the stone to a height of 12 meters above the point from which it is thrown. Now, since we are told to calculate the work, we could have used this or the potential formula directly. So now, let's go and do our substitution here. So we are going to put mass, which is 0.14 times acceleration due to gravity, which is 10, times height, which is 12. Then when we evaluate this, we get our work as 16.8 newtons, which we are going to place here. Then B says, what is the velocity of the ball at the maximum height? So let's go to the next page here. what is the velocity of the ball at the maximum height? So we need the velocity of the ball at the maximum height. Like here, this is the ground and this is the maximum height. So the ball, when it is thrown, what will be the velocity when it is thrown like this? All right, so at that maximum height there, what are you seeing there at maximum height? I'm just trying to repeat so that you see what will be the velocity at that actual height. When it reaches height, what is the velocity? All right, so actually when it reaches height, the maximum height, it stops moving. So I said at maximum height, the ball stops moving upwards. So when it reaches at this point, the maximum height, the ball stops moving. So since it stops moving, that means that the velocity is actually 0 there. All right. So since it stops moving, the velocity will be 0. So the velocity is actually 0 meters per second. C reads, on a windy day, the stone is thrown upwards with the same energy, but fails to reach the height reached area. So on a windy day, the same stone is thrown upwards with the same energy, but fails to reach the height reached area. Why does it happen like this? So the situation will be like this. This is a normal day where the stone is thrown and then comes back like this. Now I want to show you what will happen on a windy day, because wind will be blowing it. So wind will be blowing it like this. So you see what has happened. Since it will be blown, it will not reach the height it reached when on a normal day without wind. In answering, you say the wind blows the ball away from its original path, causing it to move wide from its original path and fail to reach the height it reached area on. So this is the reason. Why does it happen like this? We say the wind blows the ball away from its original path, causing it to move wide from its original path and fail to reach the height it reached area on. Okay, so let's continue. B5 reads, figure B5.1 shows transverse waves. Figure B5.1 shows transverse waves. So this is a transverse wave with the displacement on the vertical axis and any distance on the horizontal axis. Then A reads, find the number of waves in figure B5.1. Find the number of waves in figure B5.1. So they want to know the number of waves. And how do you know the number of waves? A wave is a complete cycle, or the distance from one crest to another. So this distance from one crest to another, we can call it a wave, or a complete cycle from this point where it started from. When it goes like that and comes back to this point, it makes a circle. Like, for example, you can prove if you cut this and push it here, it will make a circle with this one here. So meaning that we need to find out how many of these are here. So we can count. We have 1, 2, 3, 4, 5. So this means that we have 5, because the question says find the number of waves in figure B5.1. So it is 5. Number of waves 5. So B says, what is the amplitude of the waves generated in the figure above? What is the amplitude of the waves generated in the figure above? So for us to be able to answer the question, let's go back to the figure. So this is the figure, and we need to know the definition of the amplitude. So the definition of the amplitude says Amplitude is the maximum displacement of the wave from the equilibrium. So this line here represents the equilibrium, and the highest point of the wave is the displacement, or is the maximum displacement. So the distance is this. This is what we mean when we say the amplitude, the distance from this line to the maximum point where the wave reaches. It can be also from this to there. So how do we read? We read it from the vertical axis, where we are told this is at 0, and at this point, which is the maximum, it is at 5. So the amplitude then is 5 meters. So C reads, calculate the speed of the waves above if the number of waves in figure B5.1 are produced in 2 seconds. Calculate the speed of the waves above if the number of waves in figure B5.1 are produced in 2 seconds. So let's go back again to the figure. So here we want to know the wavelength, or the distance that these waves covered, for us to know the speed. So because we know speed is equal to distance divided by time. So now we want to know the speed, because they're saying calculate the speed of the waves above if the number of waves in figure B5.1 are produced in 2 seconds. So all these are produced in 2 seconds. And the distance they cover is total 6 meters. So our formula will be speed is equal to distance divided by time, and we'll make speed is equal to distance divided by time. And then since distance was 6 and time is 2 seconds, so we'll divide and get speed as 3 meters per second. Then B6 reads, figure B6.1 shows light in air striking the vertical side of a rectangular glass block at an angle of incidence of 60 degrees. Figure B6.1 shows light in air striking the vertical side of a rectangular glass block at an angle of incidence of 60 degrees. So this is a light striking at an angle of 60 degrees. So this is the normal. So the angle between the normal and the incident ray is 60 degrees, which is the incident angle. Then it gets there, it gets refracted, and then this angle between the normal and the refracted ray is called the angle of refraction. So there again, we are told there's a normal there, so it can also refract like that. However, this is the glass block. So we are told the refractive index of glass is 1.6. Then they're saying, what is refractive index? So here they are just asking for a definition, because here we have been given the refractive index of glass is 1.6. So here they're asking for the definition of the refractive index, which is actually the ratio of the sine of the angle of incidence to the sine of the angle of refraction. So you write as follows. This is the ratio of sine of the angle of incidence to the sine of the angle of refraction. All right, so B1 reads, calculate the angle of refraction. Calculate the angle of refraction. So they need us to calculate this angle of refraction here. So we know using the Snell's law, which says that refractive index is equal to sine of the angle of incidence divided by sine of the angle of refraction. So it's this angle they are asking us. So using this Snell's law, we should make R the subject of the formula so that we are able to calculate it. So what we are going to do is to make it like this. So we multiply by this one, n, which is the refractive index, by this. Then we get this. Then we'll divide both sides by a refractive index so that we remain with sine angle of refraction is equal to sine of the angle of incidence divided by the refractive index. So here we are also going to divide by sine here, also sine here, so that we remain with just the angle of refraction, which will give us angle of refraction, yes, is equal to sine inverse, open brackets, sine of the angle of incidence divided by the refractive index. So here what we were operating on the principle here, which says according to indices, if you have 1 over x here, it is also the same as x to the power negative 1. So this, when this sign here cancels with this, you remain with r. Then this sign, since it is down, this sign can also be written as sine to the power negative 1. Like we can write 1 over x equal to x to the power negative 1. So this is how I was able to express this equation like this. Then from there, now we are going to replace here where there's the angle of incidence, we'll put it there, and here we'll put the refractive index. So according to the information provided in the question, we are told that the angle of incidence of 60 degrees, and then here we are told the refractive index of glass is 1.6. So we'll substitute here 60, here 1.6. So we are going to have sine inverse, open bracket, sine 60 degrees divided by 1.6, which is this value replaced. Then from there, we are going to do the evaluation. After you evaluate all of this one, you are going to obtain angle of refraction as 32.8 degrees. Since our angle which we were given contains no decimal point and is just a whole number like this, so we are also going to round off this to a decimal point, because this value here is actually greater than 5 or 4, so we'll get a 1 put to 2 so that it becomes 3. Those are the rules of rounding off. So R now will be 33 degrees. Then 2 says, what is the critical angle of the glass block? What is the critical angle of the glass block? So critical angle is calculated by this formula, C, excuse me, C, which stands for critical angle, is equal to sine inverse of 1 over refractive index. So here we'll get the refractive index of glass block, which is 1.6. So we'll say critical angle is equal to sine inverse, open bracket, 1 over refractive index, which is 1.6. And then after we evaluate everything, we'll get critical angle as 38.68 degrees Celsius. Again, we'll round it, this angle, to just a whole number without a decimal point and get 39 degrees. Then let's go to B7A, which says, explain what is meant by magnetic field. Explain what is meant by magnetic field. So a magnetic field is just a region around a magnet where the force of attraction is experienced. So a magnetic field is the region around the magnet where the force of attraction or repulsion is experienced. Then here, electric field. So electric field is also an area around an electric charge where the force of attraction or repulsion is experienced. So we'll say electric field is the region around an electric charge where the force of attraction or repulsion is experienced. Complete the diagram in figure B7.1b to show the pattern and direction of the magnetic field lines in the space around the bar magnet. Okay, so this is the bar magnet with N which is north and AC which is south. So we need to write the magnetic fields here. So the magnetic fields run from north to south. So they'll be like north to south here, north to south, and also here north to south, here also north to south with the arrow there. That's how you are supposed to draw. So figure B7.1c shows a positively charged sphere placed near to an initially uncharged isolated conductor AB. Complete the diagram to show the charges induced in the diagram. Alright, so we have a sphere S which is charged, and then we have conductor AB which is uncharged. So this conductor AB is not charged, so this is a sphere which is charged. So what will happen if it is brought closer here? The positive will actually attract all the electrons to this side and leave this side be with the positive only, like this. So this is what they wanted. Complete the diagram to show the charges induced in the diagram. This is how the charges will be. B8 reads figure B8.1 shows an electrical circuit containing two resistors. So this is an electrical circuit with two resistors, and also we have this ammeter, switch, and also a battery, a source of power, which is 16 volts. All right. So A reads on figure B8.1. So draw on the circuit to show how a voltmeter will be used to measure the potential difference across the 6 ohm resistor. So they want us to measure potential difference across here. So voltage is, or a voltmeter is connected in parallel with a device whose voltage is to be determined. Potential difference here just means voltage. So it has to be connected here. And this is the symbol for a voltmeter, V, and a circle like that. So when the switch is closed, calculate the current through the ammeter A. So now, first of all, they want the current which will pass through here. When the switch is closed, definitely current will start flowing in this circuit. Now they want us to calculate that current. So for us to be able to calculate that current, first of all, we need to know the total resistance in this circuit. So we need to add these. So first of all, the formula for calculating current is given like this. Voltage is equal to current times RT. So this one is total resistant. RT is total resistant, which is RT will be 6 plus 2, which will give us 8 ohms. So here the total resistant or resistance in this circuit is 8 ohms. Then we'll make current the subject of the formula, where we'll say current is equal to voltage divided by total resistance. So we'll now get our voltage as 16 volts, and then our total resistance as 8. So we'll substitute V 16 and RT 8. And then what will happen now, when we divide 16 by 8, we get 2 amps, and the units for current is amps. So we'll put our answer there as 2 amps. Then see what is the potential difference across the 6 ohm resistor. They want the potential difference across the 6 ohm resistor. So potential difference, as usual, is the same as voltage. So this is the 6 ohm resistor here. So they need the potential difference here. So potential difference will use the same formula, which will be voltage times current times this resistor here. So the same current which is passing through here, which we calculated where here. So what we are going to say now here is that voltage is equal to current times resistor, and this is our resistor because they're saying what is the potential difference across the 6 ohm resistor. So we pick the very resistor and the current that is going through the resistor. Remember that this current is the same, which is passing through resistor, comes out here and goes the other way around. Why? Because current in series does not divide. All right, so we are going to substitute voltage is equal to current 2, because it's 2 here, times resistor 6, which is the resistor here, and when we multiply we will get our value as 12, meaning our potential difference is 12 volts. All right, so let's go. 9 reads uranium 23892 decays to form a nucleus of thorium by emission of an alpha particle. So uranium 23892 decays to form a nucleus of thorium by emission of an alpha particle. Thorium has the symbol 23490Th. So what is the meaning of nucleon number? What is the meaning of nucleon number? So nucleon number is what is also known as the mass number. So it is the sum of the total number of protons and the neutrons in the nucleus of an atom. So we'll say it is the sum of the total number of protons and neutrons in the nucleus of an atom. Then B reads, write a decay equation to show how uranium 23892 decays to thorium 23890 after emitting an alpha particle. So what is an alpha particle? An alpha particle is just a helium nucleus. A helium nucleus which consists of mass number 4 and the proton number 2. So it's a helium nucleus which I can write for you. This is an alpha particle which we write like this as symbol, which simply means a helium nuclide, which we write like this. With the 2 here as proton and the 4 here as the mass number. So this is the one which has been actually released here. So write a decay equation to show how uranium 23892 decays to thorium 23490 after emitting an alpha particle. So this will break, because to decay it is to break. When it breaks down, it releases an alpha particle with mass number 4, atomic number or proton number 2. This is an alpha particle. So now after this one is released, they want us, to write a decay equation. So they want us to write the decay equation. So the decay equation starts with this, which decays to produce this and this. Then what we will say now, we'll say, all right, so this is the general formula which guides alpha decay. So when a substance decays by emitting alpha, like we are told uranium decays to thorium after emitting an alpha particle. So the general equation that helps us to write the decay equation is this, which says if we have a parent atom here with the atomic number A and the proton number Z, and if it decays or breaks down to another atom Y here. So this Y will be known of its mass number by just getting this mass number minus 4, and also Z here, proton number minus 2. So this is actually the general equation, plus now the alpha particle, which will have 4 and 2. So in short, you subtract from this 4 and from this 2, so that new which will be formed, whatever answers you get after subtracting 4 will be the mass number here. Whatever you get after subtracting the 2 will be the proton or atomic number. So in this case, now we are going to have our decay equation as follows. So 298 minus 4 will get 234. Then 90, 2 minus 2 will get 90. Then plus an alpha particle, which is 4, 2 here, which can also be written as this. So we can also, where there's this here, we can also write sometimes this here. That doesn't matter. So this is the decay equation. All right, so thorium-234-90 decays to an isotope of protactinium Pa by beta decay. Write the decay equation to show this process. So now it is this one decaying by beta. So in the previous, we are looking at alpha decay. Now here, we are looking for beta decay. So alpha, this is the general equation. Now we are going to beta decay. So beta decay just happens when an atom undergoes decay, producing a fast moving electron. So this happens when a neutron inside the nucleus of this particular atom breaks into a proton and an electron. An electron is ejected out of the nucleus in form of an electron, and that electron, when it comes outside of the atom, we call it a beta particle. All right, so since they are saying write the decay equation to show this process, first of all we need to write the general equation which guides beta decay. So this is the general equation which guides beta decay. So if X is an atom that is decaying into Y, plus this B here represents beta decay, beta particle, which this, when it decays, it produces a new atom or element and also a beta particle here. So what does this mean? It means that if element X or atom X decays to another element Y, its mass number should remain the same. Whatever mass number this one has is the mass number this one has. So here, since thorium decays to an isotope of protactinium Pa by beta decay, which means the mass number here should be the same here. But here we are told atomic number or proton number of the new atom should increase by 1. Meaning that here if you have 90, here you say 90 plus 1, which will be 91. Then that is how the beta the decay equation for beta particle is going to be. So in writing our equation, we are going to have 23490 of thorium decays to protactinium, which will have now here the same mass number 234. Here the atomic number is 90. Here to increase by 1, plus now the same beta particle that will be released. So this is our decay equation. Then let's go to section C, 20 marks. So section C reads, answer any 2 questions from this section in the separate answer booklet provided. So here you'll be required only to answer 2 questions, and each question here carries 10 marks. So since you answer 2 questions, each question carries 10 marks. The total marks awarded for answering those 2 questions is 20 marks. So let's answer all of them here. So here C1 reads figure C1.1 shows a conveyor belt driven by an electric motor carrying suitcases into a trailer of a truck. So figure C1.1 shows a conveyor belt driven by an electric motor carrying suitcases into a trailer of a truck. So what we are seeing here is a conveyor belt here, which is actually carrying this suitcase here. So they are using this conveyor belt to load some suitcases here. So this is a conveyor belt which goes like that and comes back like this. So these suitcases, when they're placed here, this is rotating and they're moving until they reach the trailer. I'm sure if you have been to places that uses moving stairs, you understand that on a moving stair, when you step on it, they just move you using the same conveyor belts until you reach the highest or the lowest point, depending on which direction you want to go. So this is a truck here. This is a motor, electric motor with conveyor belts, putting suitcases on it. These conveyor belts are being loaded onto the back of the truck or the trailer of the truck. So let's go now for questions. Question A reads, give 2 differences between mass and weight. Give 2 differences between mass and weight. So in answering, we are going to say 1, mass is the measure of the amount of matter in a substance, while weight is the force on an object of mass. So mass is the measure of the amount of matter in a substance, while weight is the force on an object of mass. Then 2, mass is measured in kilograms, while weight is in Newton. So another one could have been mass is measured using an electronic balance, while weight is measured using a spring balance. You could also have said mass is constant at every point in the universe, while weight varies from one point in the universe to the other. So from one point in the universe to the other. So here I should have put from, a pointer here, from so mass is constant at every point in the universe, while weight varies from one point in the universe to the other. Then another point is that mass is a scalar quantity, while weight is a vector quantity. All right, so let's continue with our answers. All right, so let's go to B. B says if a suitcase of mass 20 kilogram is lifted from the ground to the truck, taking G as 10 newtons per kilograms, calculate the weight of the suitcase. So they need us to calculate the weight of the suitcase if the mass of the suitcase is 20 kg. So this is straightforward. In answering, we are going to say weight is equal to mass times gravity, and mass is 20 kg and gravity is 20 newton per kg. So we'll substitute where there is mass, we put 20 kg, where there's gravity, we put 10 and we get our answer as 200. You have to underline your answer so that the marker knows that that is your final answer. All right. Let's see. Clean up this thing here. Okay, so let's continue. Then 2 reads, calculate gravitational potential energy of the suitcase at the top of the conveyor as it enters the track. So they are saying we calculate the gravitational potential energy of the suitcase at the top of the conveyor as it enters the track. So when the suitcase, for example, this one is moved up to this point here as it enters now the trailer of the track, they want us to calculate its potential energy there. So before we do the calculation, first we need to know the formula for potential energy, which says potential energy is equal to mass times acceleration due to gravity times height. So here, when calculating potential energy, we don't consider the distance, the actual path taken by the object or by the suitcase. In this case, we will not consider the actual distance through which it moves, because the actual distance here is 9.0 meters. But what we consider when we are dealing with potential energies, we just consider the 2 levels of the suitcase from the ground to where it is now. So the initial level was here 0 on the ground. Then the final level is this trailer here above the conveyor here. So we just consider the height from the ground to the final position or level where the suitcase reaches. So we don't consider the actual. No, we consider the change in position on the earth. So the position initially, it was on the ground. Now it is at that position. So we'll consider this distance here as its height. So we are now going to calculate, to replace where there is m here, which is the mass of the suitcase, 20 kg, then g, which is acceleration due to gravity, 10 here, then h, which is 6 here. So we'll have this 20 times 10 times 6, which when multiplied will get 1,200 joules. And don't forget to put the units for potential energy. Since it is energy, the units for energy are joules. You underline it like that. All right. So let's go to C. C reads, the suitcase takes 20 seconds to travel 9.0 meters along the conveyor belt. Calculate the power of the motor. So the suitcase takes 12 seconds to travel 9.0 meters along the conveyor belt. Calculate the power of the motor. So now they need you to calculate the power of the motor, which was actually rotating, because this here, it's a line here which goes like this and also comes back like that. And those 2 circles you are seeing, those are rollers upon which these conveyor belts are placed. So it's rotating like this, trying to move these things or the suitcases up. So now there's a motor which is rotating these things here. So now, for us to be able to calculate the power of the motor, first we need to know the work which it is doing, the motor, in doing what? In moving these things along this distance here. So we know that power is equal to work divided by time. That's the formula for calculating power. So work, we know that work is equal to mass times, work is equal to force times distance. So the force is going to be given by the mass of the suitcase times acceleration due to gravity. That will provide us with the force which it is overcoming, because this motor is overcoming that type of a force, meaning it has that power actually, since it is able to move with that force. So force will be here, work here will be force times distance times, so work is equal to force times distance. Let me just indicate it so that you understand what is happening. So work alone here is equal to force times distance. Now, which is equal to force can be found by mass times acceleration due to gravity in this case, and this is just force, this is just for force. So then we'll put distance here, which is equal to, you'd find that mass is this mass of the suitcase, which is 20 times acceleration due to gravity here, 10 times distance, which is height, or this distance here, 9. So this is where this came from. So work came from here. This is how I found that. So having explained to you that, now we are going to multiply this time divided by also 12, which will give us 150 watts. So power is measured in units called watts. And then you underline to show the marker that that is your final answer. Then D says the electric motor is powered by an input voltage of 230 volts and current of 1.5 amps. Calculate the electrical energy input to the motor in 12 seconds. So they need us to calculate the electrical energy input into, they want us to calculate the electrical energy input to the motor in 12 seconds. So electrical energy is given by voltage times current times time. So voltage we are given 230, then current we are given 1.5, then time we are given 12, then you substitute and get 230 times 1.5 times 12. Then when you multiply, you get 4,140 joules. So also energy is in joules. So you have to make sure that you study different formulas for energy on electrical part of your syllabus when dealing with electricity. Also you study also different formulas for power. That is very, very cardinal. So we are done with C1. Let's go to C2. C2 reads, the figure C2.1 shows a square block of glass JKLM with a ray of light incident on side JK at an angle of incidence of 60 degrees. The refractive index of the glass is 1.50. So this question is actually similar with what we did. I don't know why the examiners just repeated the same, because for me this was just redundant and repeating the same thing, which wasn't really professional. So they needed just to look for a different question, because I think if somebody answered that question correctly, they can't fail. This would just be a bonus question on them, because repeating the same, if you go back, you find that the angle was actually again 60. So that ray, it was again light, which was incident at an angle of incidence, which was again 60 degrees, except that here they've just changed the refractive index to 1.5. There it was given as 1.6. So the calculation is similar. When they say, calculate the angle of refraction of the ray, the same formula here, I'll do it from here. So I'm just using the already made formula. So angle of refraction is equal to sine inverse open bracket sine of the angle of incidence over refractive index. When we substitute angle of incidence 60 degrees, then refractive index 1.5. So when we substitute these, we evaluate, we get the refractive angle of refraction as 5.26 degrees. Then what we are going to do is to round it off to a whole number without a decimal point. So since these two, even if we take it to 3, it is less than 5, so this value is not going to gain anything, so it will remain the same. So our answer will be angle of refraction is equal to 35 degrees. Then B, calculate the critical angle for a ray of light in this glass. So they want us to calculate now the critical angle for a ray of light. So it is always the same. So the critical angle is always the same. So critical angle is equal to sine inverse of 1 over the refractive index. Then we are going to substitute 1 divided by refractive index 1.5. Then after we do the calculation, we discover that critical angle is 41.8. Then we'll write it as a whole number. Then it will be critical angle is equal to 42 degrees. Then C reads, explain why the ray shown cannot emerge from they are saying, explain why the ray shown cannot emerge from explain why the ray shown cannot emerge from KL, but will emerge from side LM. So they are saying this ray will not emerge from this side, but it will emerge from the side LM. So the answer was that because the ray is incident at the boundary at an angle of other than, here it was supposed to be at an angle other. Here we are supposed to say, here we need to say something here, other than 90. So so this is supposed to read that as because the ray is incident at the boundary at an angle other than 90 degrees, and since it is moving from a less dense medium to a more dense medium, it is refracted towards the normal. So it is refracted towards the normal. This is supposed to be close the normal. So meaning that since it is not coming at 90, it is coming at an angle which is not 90, which is at 60 degrees to the normal. So meaning as it goes from a less dense medium, which is air, into a glass block, a more dense, so you expect this ray to be refracted in that direction like that. So it is refracted towards the normal. So this is the normal, this one, normal. They're saying diamond has a refractive index of 2.42. The speed of light in a vacuum or air is 300,000 kilometers per second. Then calculate 1 speed of light in a diamond. So here we will use another formula which says speed is refractive index is equal to speed in vacuum over speed in material. So this C is the speed in vacuum, which is this one that I've given here, of light in vacuum, or air, over this one, speed of light in material, in this case speed of light in diamond, which is a material. So we'll make V the subject of the formula. So I have speed in a material, which is diamond, is equal to speed in vacuum over refractive index. So the refractive index of diamond is 2.42. Then the speed of light we are given is 300,000 kilometers per second, of which we are going to convert this one into meters. So by multiplying this side by 1000, so kilo simply means 1000. So that we go to meters per second, because we don't record speed as kilometers per second. If it was supposed to be recorded, kilometers should have gone with hours, kilometers per hour. But what we know is that speed, this speed of light in vacuum is supposed to be 3 with 1, 2, 3, 4, 5, 6, 7, 8, then meters per second, which these guys have decided to twist it just to confuse you. So this is 1000. I've just put 3, 0, 0, 0, 0, 0, and where there's this one, I've put K and put the M, then seconds. So this can be changed back to here, and this one also can be written in standard form as 3 times 10 to the power 8 meters per second. This is what is known as the speed of light in a vacuum. So that's what we are going to use here. So what we are going now to do here is substitute. Now where there's this, we'll put a value like this one or this one, not this one. So we'll say speed here will be 3 times 10 to the power 8, which is this one, divided by 2.42. And when we do the division, we'll get a value like speed is equal to 1666942. So if we wanted, this one can be also written in form like this, as speed is now equal to 1.2 times 10 to the power 8 meters per second. So what I did here is just to get a decimal point from here, move it to 1, 2, 3, 4, 5, 6, 7, 8. Moved it here. So then I had now 1 point. Then I just decided to put one letter here, which is one digit there, which is 2, then times 10 to the power, since we are moving how many times? 8 times to the left, so the 8 will be positive. Then I had to bring back the units for speed, meters per second. So that's how this was found. All right, so let's continue. So at this point, if you are finding a value, please, I ask of you to like the video. Also, if you haven't yet subscribed, to consider subscribing to this channel so that you don't miss on my next video, which will be dealing with the Science Paper 1 GCE 2020 and also Science Paper 2 GCE 2020, which I'm likely to release in the coming few days. So let's go to 2. They are saying critical angle, so we calculate the critical angle. So as usual, critical angle is equal to sine inverse over refractive index. So we'll substitute refractive index is 2.42 of diamond. Then after doing everything, the answer goes to 24 degrees. So let's go to the last question, which is C3. We have come a long way. So C3 reads, the atomic number of americium atomic number of americium 241 is 95. Americium 241 decays by losing an alpha particle. So it decays by losing an alpha particle. Then they are saying A1, explain why smoke detectors containing americium 241 are not harmful to people. So they are saying, explain why smoke detectors containing americium 241 are not harmful to people. So what you should know is that this americium, since it decays by losing an alpha particle, it is a radioactive atom. So since it is a radioactive atom, that means that it is somehow dangerous. Radioactive atoms are dangerous. So radioactive atoms are dangerous. Now, since they are dangerous, however, the one that releases an alpha particle is used in smoke detectors. So these smoke detectors are used as automatic switches to tell you when there's smoke. For example, what they do here, they put, for example, there'll be a source of a radioactive material here. They'll put a radioactive material here in a building, maybe in the roof. Then on the other side here, this is an enclosed container or just an opening. Then on this side, they'll put what we call a detector. So here, there will be a machine that we can call as a detector. So this one will be detector. Detector, sorry, it's difficult to write using this mouse. It's not made for writing this software. So this one is decaying, producing alpha particle. So these alpha particle, when they come here, they ionize some, they pass here. When they pass here, they're being emitted here, they pass here and they are recorded. Their presence is recorded by the detector here. So when they are emitted, they pass, they come to the detector here. That's what happens in a smoke detector. However, if in the building there's smoke, when smoke passes here, if this is smoke, when smoke crosses this distance or space in between the emitter of an alpha particle and the detector, it will block these alpha particle from reaching here. So when the smoke blocks the alpha particle from reaching the detector, so this now is going to trigger an alarm. So there will be an alarm here in form of a speaker here now, that is going now to produce sound. So that sound now is going to alert the people that this building is about to catch fire. So that's how a smoke detector works. That's what they're saying here when they say, explain why smoke detectors containing americium 241 are not harmful to people. So since they release the alpha. So here, for you to answer this question, you have to look at what alpha particles are in terms of their characteristics. So these, we call them that they have what we call less penetrating power. So less penetrating power into tissue, meaning they don't enter into the body, because radiation by nature is dangerous. When it enters your body, it changes the makeup of your body, because we are made up of atoms as well. So those particles can knock off electrons from our atoms, and they can cause mutation into our makeup, the way we are made up. So they can bring cancer, because they will disturb the normal functioning of our body, and they can cause our body to start functioning abnormally, like in the case of the nucleus, or I mean in the case of cancer, which is the abnormal division of cells. Cells, as we grow, they have a program which tells them how they should divide. But during a cancer, cells just divide abnormally and randomly, and at a very fastest speed or fastest rate. So those are some of the effects that radiation can cause. Now, in this case, this type of radiation, like alpha, since it has less penetrating power into tissue, it can't go into our body. So it has less penetrating power. So it is not dangerous. Why? They are saying explain why smoke detectors contain emission 241 are not harmful. So one, it has less penetrating power. So let me see the question that I had, the answer that I actually had to put. So where are my answers? Okay, yeah. So number one, yeah, we are on number one actually. Explain why smoke detectors containing 241 amnesia 241 are not harmful to people. So I said because it emits alpha particles that travel a short range in air. So alpha particles, they don't have a long range in air. Then two, have less penetrating power in tissue. So these, when they come, even if they may reach your body, they don't have power to enter the tissue of your body, because we say these, they have less penetrating power. They can be stopped by just a thin sheet of paper, just a simple paper like this one here, can just stop them from going to the other side. So, and also they move a short distance in air, so that is why they are not harmful. Then here, 2 says copy and complete the equation showing this decay by giving values for x and y. So since this one decays by losing an alpha particle, so meaning it decays by alpha. Again, this is what we did. So they were just repeating the same stuff. So if you failed that other part, if you found it hard, then this one will be hard as well, which was really very, very unfair. So here, what you are going to do to answer this question first, you need to write the general equation that guides decay by alpha. All right, here I left out a 2. How did it remain? A 2 here. So, yeah, so let me get my highlighter. So, this is the general equation which guides us. So, they are saying we copy this one and complete it. So, now we will make sure that this will remain the same, since this is this malicious, then this is this, then this now will be actually this one here. So meaning we'll say 241 minus 4, which will give us 237. So on this one we'll have 237. So you say 241 minus 4, you have 237. then 92 minus 2, you have 93. So that will be our equation. So this is our complete equation, just as I have explained. Then let's go. B says figure C3.1 shows how the activity of a sample of americium 241 changes over a long period of time. So figure C3.1 shows how the activity of a sample of americium 241 changes over a long period of time. So the activity is actually the rate of decay. So activity, we call it the rate of decay. So this word activity is rate of decay. So now it is also, we can also call speed at which an atom breaks. So it is the speed at which an atom breaks. So activity is equal to rate of decay. Sorry if you can't see, but just follow me. Or speed at which an atom breaks. So that's what it means by activity. And you know, in radioactivity, because this question is coming from radioactivity. So in radioactivity, what happens is that atoms breaks. By definition, radioactivity, the term radioactivity means the breaking down of atoms. So radioactivity is the breaking down of atoms. That's what it is. So now, atoms break when we are dealing with radioactivity. So if atoms are breaking, the time they break per second is what we call activity. Or when we compare breaking per time, we call it activity. So that's what it means when we say activity here. So atoms break. So now I want you to understand this so that you never get confused with this. So what it is here, sorry for delaying, I have to just make sure you understand. So what it is here, they are showing figure C3.1 shows how the activity of a sample of americium 241 changes over a long period of time. So it is breaking. So this is the activity. So at 0 time, or at the beginning, when time is 0, meaning at the beginning, before they started recording, they discovered that the speed at which it was breaking was at 64, which they have said counts per minute. So it had 64 counts per minute. Then after time has passed, time is in years, after 500 years, they discovered that a particular activity of americium, we are dealing with americium here, shows how, let us read it properly. Figure C3.1 shows how the activity of a sample of americium 241 changes over a long period of time. Yes, so at 0, it was in 64 counts per minute. Then after 500 years, the activity was 30, meaning that's how it was breaking. After 1000, it was 14. After 1500, it was 6. After 2000, it was 2. So the activity was decreasing. It was breaking until maybe it changes completely into other atoms. Then now, here they're saying B1, use these numbers to draw a graph of activity against the time for americium 241. So 4 marks. So we need to draw a graph which will be like this. So I had to draw the graph here, where if this is the time, which is supposed to be the vertical axis here, then this is the count, which is supposed to be the horizontal time, then the vertical, the activity. So I had to plot here, for example, since time is on the x-axis, so I'll say 0, 64. So 0 is here, 64. So I go, this is 60, 62, 64. I put a point there. Then I come back again, 500, 30. So I come to 500, it's this point, 30, it's here. This is where 30 is. I put a point there. Then I come again to 1000, 14. So 1000 is here, 14 is somewhere here. So this is 10, 12, 14. So it's here. I put a point. Then 1500, 6. So 1500, 6 here. This is 246. So this is 6. Then this is 2000, 2. 2000, 2. So this is 0, 2. 0, 2. I put a point there. Then I draw a curve, a smooth curve like that. All right. Then they say, so 4 marks there. So you have to label. Make sure the horizontal axis, you label it time. Then the vertical axis, you label it activity, count per minute. Then the graph itself should also read activity against time, because that's what they said. Use these numbers to draw a graph of activity against time. So it needs to have a title. That's when you can acquire all the 4 marks. So 2 reads, use your graph to find the half life of americium. So we use the graph to find the half-life of americium. So half-life is the time taken for half of the amount of a radioactive substance to decay. So we'll go to the graph. When we come to the graph, activity behaves like the amount that we have. So we had the initial amount was 64. So from here to here, 64 is here. So half of 64 is actually 32. So we come, half is here, 32. Then we draw a line, a dotted line towards the curve. When it strikes the curve there, then we drop it down straight up to the time where, up to the point where the time is. So here we'll just approximate. Since these lines here, they represent 0, 100, 200, 300, 400, 500. And this line seems to be in between. So half-life here should be 450. So half-life should have been 450. All right. Yeah. So half-life is 450 years. Then let's continue. So California 241 is also radioactive and decays by losing an alpha particle. It has a half-life of 4 minutes. Suggest why it would be unsuitable for use in a smoke detector. So this one won't be suitable for use in a smoke detector, for reason being that since it has a short half-life, that means that it will number one run out of itself, because after 4 minutes it will be breaking. So if this is the source itself, which is California here, and this is a detector here. This one is a detector which is meant to sense, and it has a connection here to a speaker that is supposed to produce some sound here whenever this detector actually senses that there is no radiation coming. So what happens is this detect this source here, which is, if it is made of California sea, so it will be emitting alpha particles that will be coming this way. Every 4 minutes it will be make sure emitting particles that will be coming this way. So as they will be breaking these atoms coming this way, after 4 minutes they'll be breaking, which means that after 4 minutes atoms here are breaking, and many of them are actually breaking. So if they are breaking many of them, it will take a short period of time before this material here can run out, which means after it runs out, it will even give a wrong signal here, which will make this alarm sound, because once it has run out here, it will show as though there is a smoke here which has blocked the passage of these alpha particles reaching here, which will trigger this to make a sound which will be actually giving a false reading, because it will run out. Then the other problem is that you need every time to put it here, so it is not good for long-term use, because these smoke detectors are inserted maybe in the roof of the room for a long-term use. They stay there. So if these detectors, they are using this californium, which has such a short half-life, they need to be replacing them time after time for the detection to be there. Otherwise they will not offer detection. All right, so according to the answer which I gave here, guys, I said what I said here, let me remove this trash here. Okay, so what I said here is that because it has a short half-life, which means that it cannot offer detection for a longer period of time, since after 4 minutes it would have decayed, which means that you would need a large amount of the sample if it were to be used. All right, so that's what I just had to put there, guys. So let's continue. I think at this point, guys, we have come to the end of the lesson. All right, so thank you for watching, and see you in the next video. All right, guys, I thank you very much for watching. Again, subscribe to remain connected to my YouTube channel. All right, so this is how you subscribe. Press on the subscribe, turn on the notification for you to be able to see my next video. Guys, goodbye, and see you in the next video. Peace.